I invite Professor R Madhav for the next lecture. Before that, let me introduce Professor Madhav. Professor Madhav is a distinguished visiting professor of AICTE-INAE, visiting professor IIT Hyderabad, and most importantly, is an alumnus of Andhra University who is host the conference. He graduated from Andhra University in 1960. And Professor Madhav's research interests span the whole gamut of geotechnical engineering. He has guided more than 45 doctoral and several master's theses. He is a fellow of Indian National Academy of Engineering. He was awarded with several awards of IGS and Distinguished Alumni Award from IISc Bangalore, Doctor of Science Award from IISc Bangalore. He is a very well-known teacher and a researcher who traveled extensively all over the world, delivering lectures, keynote lectures, invited lectures, and the list can go on. But to keep with the time, I request Professor Madhav to share his knowledge on mitigation, prediction, and limitations of Scour. Welcome, sir.
Thank you, Ramana. Can everybody hear me?
I'm able to hear you. Yes, sir. Yes, sir. And your video is on, sir?
It's on? Can you see?
Yeah, we are able to see you, sir.
Okay.
Okay, sir. Yep. Go ahead, sir.
I'd like to thank Professor Reddy for inviting me for this very important workshop. To me, it's one of those most timely ones for the simple reason. In India, very few seem to have been working on this Scour. We left it to the hydraulic engineers to decide, and we are not able to modify the predictions or in terms of limitations of the present method. As we go along, I would like to highlight where the lacuna are, and I would like my young researchers to take this topic for future work for the simple reason it's the most challenging one. Just as we have foundation, soil foundation interaction or soil structure interaction, we have an interaction problem between the water or the hydraulic part and the ground. And we somehow seem to be a little scary of getting into this area. And I haven't seen much work to quote in terms of prediction of Scour. And while we are trying to solve the effect of Scour, like what G100 in terms of design, etc. So what I'd like to now go into would be initially, I had a very interesting experience of dealing with the coastal Scour. And for the last 10, 15 years, I've been trying to deal with alluvial Scour, wherein the practice is very, very conservative. And that way leads to enormous expenses, time, etc., which is something not very good. My first project I would like to talk about is the Gulf of Cambay on the west coast, slightly north of Mumbai. You know, we in India, we have tidal effects, but on the east coast, I believe the tide isn't too much, about a meter, meter and a half, whereas in the west coast, it could be like slightly more, 2.5. But in Gulf of Cambay or Kambat, as they say, I believe the tide could be as high as 5 meters or so. So somewhere in this region where there is enormous erosion that's taking place. You know, this has been going on for quite some time in the recent past. I believe the coast was moving at the rate of something like 5 to 10 meters per year. And on the right side, you will see that there is a oil field, which is ONGC is buried. And you can see the coastal erosion because of the high tide. Apparently, the tide velocity could be as something like 4 to 5 meters per second. So it could be very, very significant. And this problem they were trying to deal with various aspects of it. You can see how the erosion takes place over a period of time. And they were trying initially to do various kinds of sheet piles, piling, trying to stop the erosion. And all of them seem to be collapsing within a matter of months. And the erosion has reached such a stage As you can see on the right, there is a small shipbuilding yard. This is what they call as the small ships, which are 1,500 to 2,000 ton capacity, which they call them DHO in the area there. And this has been used for the last maybe 2,000 years for trade between India and the Middle East and the Arab countries, Gulf countries, and that is getting eroded too. You can see very close to the shipbuilding yard, erosion has reached. And this is another closer view. In a matter of probably few months, a year, even the building that you see here would be gone if we don't do something else. And you can see the piles which are already installed completely eroded, even the reinforcement, probably because of the cost, what is it? Seawater effect has eroded and is being visible there too. Another closer view of the same shipping building yard. And this is where we were asked to look into it. And then it's such a challenge. We hardly had any information about the soils at the site. They hardly could get us any soil sample. All we could find out was it's predominantly a silty sand, and the tide effects are very, very significant. So we had to make a guess, what can be the possibility? So after a few iterations, we came with this solution. We said the only slope that will be possible would be 2 horizontal to 1 vertical, but that we protected significantly. So we provided a geotextile as a separator and for erosion protection. Then we provided a series of sandbags, on top of which we provided gabions. The height of the slope was fairly high, so something like 10 to 12 meters. So we had to provide berm at a height of 7 meters. And then on top of it, we put the gabions and tied them too. But the most significant one we thought was, it is not so much the slope erosion alone that bothers. We need to worry about the base too. So we had to provide an apron which goes something like 12 meters into the bottom of the bay or the gulf, and then we had to tie them. So the solution provided was a combination of both gabions and geosynthetic with sandbag particles, the geobags put in. When we are trying to look at the gabions, it turned out that normal ones will not be more valid because of the salt water and erosion of the ordinary galvanized gabion. So we had to choose for pre-coated ones. And the other interesting thing is you will not get any dry surface to put in. So everything has to be constructed in water, so through barges, etc. When the course, they gave us about 850-meter long course to treat, and other places the height was a little less, so we didn't use the berm at all. But the base 12-meter apron was necessary. The reason we were insisting on the apron was if there is any initiation of the scour near the slope, the apron would automatically sink, go and seal the erosion. And this is how the design was approved, and then we installed it using barges. And I would like to say that originally when we started, it was sometime in December 2006, April, this work started and the gabions were put in. And this is how in May it looks like. The tide was coming, but the gabions were holding more or less. And then we went on observing it over a period of time at different times of the tide, up and below. And in spite of the tide being active, it has been working. And you can see even after 3 months, we are able to protect it. And the idea is that this will last for about 5 to 10 years. That's what they wanted. It's not a permanent solution. But what we found interesting after 3 months was, instead of erosion, there is some accretion that is taking place. When the tide goes down, you can see the soil getting deposited and giving additional protection for this too. This is after about 4 months of this, and you can see the same course continues to be. And the people came to check. This is being chased from ONGC, and apparently they were trying to extend the same treatment for the rest of the bay over which their oil field was being extended. Their oil wells were getting affected very quickly. And this is another view. You can see And then what happened was that whole thing seemed to be working well. I couldn't go this year, but apparently till last year, it is still working very good. And this is the extent of our area they gave for treatment. And here you can see the depth of height of the embankment is not that high, so we didn't do with the bumps at all. But you can see the geobags that were put in there partly, then the geocell, the gabions, etc. And you can see the accretion even here when the tide goes down. So this seems to be a kind of solution which worked here in this particular case with limited geotechnical data. We had to base it basically on some intuitive angle of shearing resistance. We took maximum maybe about 25 to 30 degrees, and the gabions seem to have prevented further erosion. So this is one of the most satisfying jobs we are called upon to deal with limited information. I would like to now come to more challenging jobs which I've been dealing with for the last 10, 15 years. A lot of bridges in India are being designed, and the Scour is a major problem, as being highlighted by several people, including Jihan. The problem here is that our IRC code is very, very conservative and is probably, in my opinion, very outdated. So I wanted to impress upon our young engineers what is that which controls Scour. I will first look at the substrata. You need to have a series of borings done and get the boring data, stratification. Then we need to know the bed material, the side gradation, distribution, etc. Then the stream and plane cross sections are very important. And what will be the shape of the platform that you're taking? And then again, the watershed characteristics. In India, we have the alluvial rivers in the north, which have very high flood level, whereas in the peninsular India, we have a couple of or few major rivers, but a lot of others are minor ones, and there are even small streams where there could be a flash flood. Then we need to have Scour history, which unfortunately is very, very limited in our country. I haven't seen much of data over a period of time. Then we don't even look at the energy gradient in the sense that how is the bed slope? If I have a obstruction, what will be the gradient upstream and how is the gradient downstream of the bridge, etc. Then history of flooding. What is kind of, is it one day? Is it over a period of a month, or is it a flash flood, etc.? Then location of the bridge. I believe now there are several bridges parallel to each other being constructed in several rivers. For example, if I look at Godavari, there are 3 next to each other. What would be the effect of one on the other? Are we taking that into consideration? Then the stream. This is where I found very interesting thing. Some could be perennial, which means the water is there all the time, flashy or intermittent, or there could be a gradual increase in peak. That's a different one. The geomorphology, in the sense that you have the Himalayan fed rivers, which are geomorphology is very, very different. Or geomorphology is different because what we have here is a different kind of soil, mostly weathered soil from the granite, basaltic, or sometimes if you look at the Western Ghats, you will get some kind of lateritic soil. And those are the ones which are controlling the Scour. Then erosion history. We have hardly any idea, no experimental data, no published one. Maybe the hydraulic engineers have some information, but as far as I'm aware, geotechnical engineers are not aware of any of these. Now the complication now is sand and gravel mining. I think somebody is using his, I think it better. Can we request the participants not switch off
somebody using that touchpad?
Then off late, we are having a major problem in terms of mining of sand and of course gravel, and everybody knows this makes a big difference in terms of Scour.
Sir, you can deactivate the annotation, sir. You will have more options.
I think, okay, basically I wanted to show that it takes different types of soils. You have scouring. In case of granular soils, it can be hours. Clays, it could be day. And depends also what kind of water. Is the water clear water, which means there is no bed load, or if there is some live bed, then you have a different kind of thing. Are we aware of these effects in calculating the flow? Then it depends on the depth of flow. You can see if I have an axisymmetric pier, the kind of effect of water depth and the kind of vortices and the flow field changes and the turbulence that takes place. So it makes a big difference in terms of the depth of flow around the pier. This is for a simple circular pier. The same mode, if it's a narrow one, you can see at the bottom what can happen in terms of formation of a scour hole. And then because of that, the kind of vortices that form and further propagation of the scour bed. And you can see, I would like you to also see the velocity profile, which increases from the bottom of the river to the top, and near the bed, obviously, there is some very low velocity that leads to some shear stress too. This is how you can see flow field around a wide width pier. And it's very different from what you have seen for a axisymmetric narrow pier. Now, do we use the same Scour equation for both of them? Or should we say we need to consider the size of the and shape of the pier? This is what bothers me in all our design analysis for the Scour. Then this local Scour, which I think Jihan also mentioned several ones, but I would like to know what kind of mechanisms hold good. If it's an accelerated flow, which means the flood is increasing, or is it a secondary flow, which means because of all these horseshoe vortex where you have a horseshoe kind of thing, or a surface one, or a wave, or a pressure gradient, all of these make a difference in terms of the Scour. Basically, what I would like to know would be, if I have a flow occurring, what would be the shear stress that is going to cause the Scour? Which means I need to find out the bed shear stress, and we have to ensure if this bed shear stress is less than the shear resistance of the granular material. If not, the Scour will take place. So this is how what can happen if the bed shear stress is greater than the shear resistance of the soil at the base. And we haven't been able to use any of these in our prediction of the Scour depth. So these are again flow fields around local Scour problem. And I would like this to be analyzed in terms of geomechanics. And these are again the processes you can see with the kind of vortices, the rollers at the surface, and you can see the horseshoe vortex at the base, which I mentioned a bit earlier. And this again, I think Jihan mentioned it already, the kind of shape at the bottom, you can see the Scour is biased, but the slope below before that gives you the kind of Scour getting initiated, and everything depends on what you can call as the median grain size for the soil there. The point I'd like to mention is from hydraulics and geomechanics, you can say the Scour is a function of several parameters, including unit weight, the particle size, effective stresses, specific rate of soil field, the water depth, the width of the pier, the height of the pier, the velocity. We can even analyze using dimensional analysis. This I'm presenting for the simple reason I want to know how many variables are available for us to analyze and use in terms of predicting the Scour. Unfortunately, we don't do that. This is what I got from the Federal Highway Authority, wherein they use what's called Shepherd's equation, and then the Scour, which is normalized with respect to effective diameter of the structure, which is equivalent to a circular one. It depends on the water depth, a function of it. It depends on the velocity with respect to the critical velocity, and it also depends on the relative size of the pier with respect to the particle size too. And these are all functions which are fairly involved in terms of various parameters. You can see that in case of clear water, when the velocity is less than the critical velocity, or if you have more than, you will have another set, you will find that these equations are all given so that I can calculate the Scour depth based on these parameters. And this is how the subject has evolved in terms of hydraulics, but in terms of our prediction in India, it is rather sad. This is for the live bed scour, wherein the velocity could be higher, in which case the scour takes place along the base, and you find that the equations are more different from what we have seen earlier. So this I find is a more challenging job, and we need to do that. And then how do we take care of the prediction and protection? So once you get the scour, I mean, in terms of the equivalent diameter, what could be the maximum? And I want you to see here, the maximum scour in clear water is taken as twice the equivalent diameter of the pier in case of clear water. And basically D is the effective width, you can say. And then in live bed, which is the big erosion taking place, it's about 2.2. This is how Federal Highway gives you. And the bed shear estimate is given in terms of the velocity and Ks, which is a bed roughness coefficient, which is a function of the particle size. If the particle D50 is more than 0.8 mm, or if it is in the range of 0 to 0.8 mm, we have different values for the bed roughness. So you do get a bed shear stress available for us. And then based on that, we can also calculate the design shear stress, which is a function of, here again, I want you to see there is a parameter called KB, which is a bed coefficient. So is the river straight or is there a bed at that time? And then of course, it depends on the hydraulic radius, area divided by wetting parameter, unit weight of water is the gamma standard. The other important thing I would like to do is the slope of the energy gradient, which means at the bridge, what will be the gradient before and after the pier. They find out the gradient, and then you can estimate the bed shear stress. And then we compare that with critical shear stress as a function of grain size. And here, like this is a very, very important parameter. When you look at the mean grain size, the lowest critical shear stress which the soil can offer is with respect to a granular material, probably 0.4, 0.5 millimeters in diameter as a D50. And as the particle size increases, the shear resistance increases, obviously. But on the lower side, as far as sands are concerned, I mean, below 0.1, 0.05, etc., you have the V-shaped curve. But when you come to the silt fraction, or even part of the clay fraction, it's not all that simple. The variation in terms of critical stress, which will cause erosion in case of silt and clay, is very uncertain. It can vary from as low as 0.5 into D60 to the power of 0.4 to 206 into D60 to the power of -2. So this is what you have from the Federal Highway Authority. And I would like you to realize that the shear stress which causes scour is different, I mean, in the sense that resistance is very different for silt and clay, and you cannot use a simple equation at all. And that is where it matters. Obviously, in case of intact rock, etc., it's very high, we are not worried. And as you can see on the right, if you put repair, there is no worry about in terms of the shear stress kind of thing. So then I wanted also looked at the CELIA, that is the British Construction Industry Research Association. They also said that in the bed is ratified, each area should be considered step by step, and it's likely to terminate or progress to the next. Why I'm insisting is that I have many places where the surface may be fine sand, but if I have sand or gravel, I know that scour will stop. But unfortunately, the code doesn't have that kind of thing. And I have problem with many practicing engineers. The British engineers say, no matter what it is, you have to use the scour depth predicted by the sample near the bottom of the river bed. This is another parameter that seems to be is the pier nose and shape configuration. Suppose you have a flat one, like square nose. Round is very common for us. That is, if you have a double D, you have the round nose, a cylindrical circular pier. Some of the old piers had this wedge shape or bevel shape, which you can see as D. And then, of course, you have piers which are multiple, that you have two individual ones on which the deck is cast and we built it. This pier nose also makes a configuration in terms of Scour. Then I think Jihan talked about piles, and when we have these piles, we have the group effect, then we have the pile cap effect. Pile cap also is affecting the flow, and below that is the group of piles, and the pier is above the pile cap. So all these three have to be considered: the piles, the pile cap, and the pier in terms of the rotor. Because of them, you may have three different aspects of Scour. We look at the Scour due to pier, Scour due to the stem, or due to the pile group. And when we have pile group, sometimes, we haven't been using too many of them, but off late, we are getting into using piles. Otherwise, till now, in India, we have been using most of the time well foundations. And which are, in my opinion, very conservative and then very time consuming. We should go away from well foundations to the pile groups, which we have enough technology to install and then analyze too. I think, G about when do I consider if the spacing is close enough, can I use a kind of block failure or block of flow and then do the Scour for the pile group? That depends on the spacing and you can design accordingly. Then this also gives you kind of erosion rate, but as you can see, the fine poorly graded sands and silty sand are the most highly erodible. And erodability decreases, rate decreases as you increase the kind of soil becomes sand or low porosity, silt, jointed, etc. And this is very important in the sense how a graded sand or silty sand, but I don't think it's necessarily true for all other kinds. So have we taken that into consideration? And then here again, I would like you to look at effect of the flow depth with respect to pier width and what is being observed over various results that we have, and the Scour in terms of pier width again. And as the ratio increases, there seems to be a tapering off of limit. Scour depth is limited to maximum 2.5 to 3 times the pier width. Whereas if you look at the Chitale one, it shows linear, which is very, very highly over predicting the Scour depth with respect to flow depth, which to me again is a very serious limitation in our design. And this is the profile.
Scoring and
I
erosion.
request all the participants to mute themselves. Thank you.
Then I found that very interestingly, in our IRC, we are assuming a profile which is given at the top, wherein the riverbed is more or less constant over significant part, and then of course towards about 22. Whereas I find that many of the channels where the flow is occurring in the peninsular India, you have a channel which is relatively narrow, and then you have a right and left overbank. If that is true, if N2, which is the channel width, is relatively small with respect to the total width of the river, then how do we design in this case? Should I use the same Scour for all the reaches or from left abutment to right abutment? That is another problem we have. Then you can see the effect of the flow velocity, and you can see the difference between the two. When I look at the velocity contour, they're very different depending on the shape of the river channel. We haven't included any of these parameters in our design. This is a typical bridge profile, and I can show you that this is not very uncommon. Many of the sites where we have seen the fine sand or the erodible material is at the center, but we don't necessarily have the same thing. Now, coming to IRC 78, which is what we are using in all our design and where I find many challenging jobs of trying to get to reality. They have only 4 categories of catchment area. 0 to 300 square kilometer, 3,000 to 10,000, 10 to 40,000, and above 40. And then they say increase the discharge. The Scour depth is predicted based on simply the particle size and the shear KSF factor, which is a shear Wurtzite factor, which is a function of the mean diameter of the particle. That's all the information that's being included. And unfortunately, this is a 1940 based equation, which is being used in our present day design. We have changed since then. And these are the silt factors as a function of particle size. Is that enough to predict it? What I'm surprised is, why should I only look at the particle size that near the top, not at the bottom? We have to be very whole. And this is the present state of design in terms of based on IRC. This is Federal Highway, where they try to predict, as I mentioned earlier, on several factors. The Scour depth, the function of flow depth, factors for pier node shape, angle of attack of flow, for bed condition, pier width, length of the pier, shroud number, mean velocity, etc. Where is this state compared to our IRC? So we did a project where there was a bridge in one of the North Indian states. They were putting the pile foundations, and they were saying the piles had to go deep because of the prediction of Scour. And this is a fairly long bridge, as you can see. There are about 12 to 13 spans, and the pile groups were varying from a 3x3 to something like 4x4 and 6x6. I wanted to look at the ground profile they had here, and I want to see here, when I look at it at a depth of 12 meters, I got a intermediate geomaterial, which means it's a kind of bonded, what should I say, cemented sand, which is not plastic, and the N values are more than 200. Which means actually recovery, refusal. N values are increasing from 10 to 30, 40. And I want you to also look at the fines fraction. At the top, I have 46% fines. Then at a depth of something like 2 meters, the fines content comes down to 22, 10, etc. And as you go deeper, the fines content is maybe 10 to 14. But I want you to look at the intermediate geomaterial, which is a very strong, stiff material. And this is the bridge side. Another profile with the same, very similar. And I get again the intermediate geomaterial at a depth of 13 meters. And the fines content, except at one particular place, it's all very low in this case. And here is the grain stress distribution. As you can see that most of the soils are on the, the sand, fine sand medium. There are few samples which are on the fine side of it. And based on that, they are trying to calculate in terms of discharge and the Scour. And the hydraulic engineer gave this calculation. And he gave a Scour depth of something like 13.75 meters. This is the prediction, which means normal Scour depth. And then we had to provide for twice that. So which will become 27 meter is the depth for which we had to assume no lateral resistance, no pile capacity, etc. This is the sad state of affairs that we have. The prediction is 13.76. I want you to look at the intermediate material, which is available at 13 meters. Do you think the Scour will progress from the top to below the intermediate material? I have also found that there are sites where even if the hard rock was made, that was in somewhere in Orissa, they were insisting, no, you had to take the piles much deeper as per the prediction based on whatever is available at the top. So we had a lot of arguments trying to convince the Scour in a non-homogeneous media, you had to analyze separately for each layer. Nobody does it. This is how they have been saying that you had to increase the maximum depth of pier depth for Scour for pier is twice the predicted Scour, which is 13.76, and for the abutment they said 1.27. This is what our IRC says, and we had to convince the people not to go for such deep piles. And then we don't need to provide such deep piles for abutments because the North Scour strata is available at a very shallow depth. I mean, very close to the abutment level. So we had to talk to them saying that we need to revise the whole thing. And look at this. Because of this, the piles had to be taken much deeper and the pile capacity is high, I mean, very long. And then the socket length has to be increased to take care of both axial and lateral loads too. I want to finally give you a thought for remembering. If I do a hydrometer analysis, and if the flood comes and recedes, where do you think fine particles will be? Will they be at the bottom or do you think will be at the top of the sediment? So this is the point on which I want you to think and then see how much can we modify our design in terms of predicting the Scour depth as for the based on geotechnical consideration. The flood is coming. It is bringing a lot of bed load and the soil is getting churned completely and the flood recedes. And once the flood recedes, the coarse particles will settle down first and the fine particles settle later, as you have seen in the borehole data. If that is so, and if I determine the D50 for the fine, for the particles at the top, should I use the same D50 for all layers? Or should I say I need to work better in terms of stratification and recalculate for each grade, each depth of the river bed? This is my thought for everybody to look into, and I encourage all the youngsters to work on this kind of problem. Let's work with the hydraulic engineers and bring in some geotechniques in Scour depth prediction. And of course, we know enough to design once you know the Scour depth. But my main concern is how to predict Scour depth. I would like to thank all of you for your patient listening. And I would like to end my presentation with usual signature. I find that geotechnical engineering is a science, but when I'm practicing, it's an art. I cannot use any of these equations when I'm practicing my geotechnical ones. And I hope I have illustrated the challenges we have. Thank you, all of you.
And there are a couple of queries here. I'm going to read out for them, sir. These days we are getting Scour depth as high as 20 plus meters. How do we mitigate? We prefer well foundations. However, right now it has been mentioned to avoid well foundation and go for piles, which becomes very costly.
I would like to say that well foundations have been traditional in India. We have been using them from the time of Taj Mahal, which was built on well foundations. But let me tell you, does anybody know how conservative is well foundation? We design according to IRC code. But the process of sinking itself changes the properties of the soil. So we hardly know anything. And we had used them because the technology was not available. We knew how to sink a well for our drinking water, but it doesn't mean that it's good for structural ones. We did it. But since around 20 years, maybe last 15, 20 years, we have very good equipment for pile foundations. Let me tell you, pile foundations are very quick to install. The quality is much higher and much cheaper. You can save a lot of time in construction if you go for pile foundations. Every project which has well foundations will drag on to 5 to 7 years. And I don't know how many of you are aware that sometimes because of the intermediate floods which happened in the second or third Ganga bridge near Patna, even the well got washed away. So I had to reinstall it. I had done another project where the wells got tilted and shifted. And if the well gets shifted or tilted, its capacity is lost. How much can you expect it to take care? The limit is something like 5 to 8 degrees maybe, but even then the capacity is reduced. So to me, just as there is no one who doesn't use a smartphone in these present times, you should go for pile foundations and not go for old the well foundations, which are like our earlier for mobile phones, which are very primitive. That is the best analogy I can give you. And high time we go, because the equipment for pile foundations is fantastic. In the Deep Foundation Institute meeting, if you remember, they even use the continuous auger piles, which are very fast to install and very reliable too. So that is my advice. Don't go for wells at all.
Okay, sir, one more question. How can we arrive on the silt factor for intermediate geomaterial?
There is no need, actually. Honestly, I want to, my whole presentation is, you can see, the scour depth somebody mentioned is 20 meters. Is because at the top we have more fines. Basically, if the soil below is, once it covers 1 meter, 2 meters, it meets with a much stronger or much coarser material. Will the scour progress? Where is the prediction of 26 meters? How did it come? Is it because the grain size at the top, or is it grain size right at the bottom? That is where I mentioned, according to Syria also, you initially predict, but once you go 1, 2, 3 meters, you will find the grain size distribution is different. So it can cover up to 2 meters, 3 meters. It meets with a coarser material, a stronger material. It will not progress further at all. We have been asking, even I was at IIT Kanpur, I asked the RDSO, can you give me a cover of all the bridges you have? But they have not been able to share it with us. So the biggest problem is we are still following the same old Lacey's equation, which he, if you go to the history of it, he worked in Punjab in 1920s and 30s. And the oldest reference, which CBIP manual also gives is dated 1941 for scout prediction, and which is used in our IRC. Please revise it. I want my young people to work on, suppose I have a bed which is stratified. I have fine sand, coarse sand, and coarser sand below. Run a scour analysis or scour experiment. Will the scour progress from the top to the bottom if the increasing particle size is increasing? For intermediate materials, for rock, etc., scour is, as I gave you the shear resistance is so high, it will not scour at all. So you calculate what is the bed shear and what is the shear resistance of the bed material. And if you find that the bed material is stronger than the bed shear, no scour. So basically, people had to realize, don't depend on one D50 for the soil at the top of the riverbed. Go for a stratification analysis and make sure. And then we save a lot of money for our country. If only we go for a stratification analysis and improve our scout prediction. And I find this is the biggest problem. I had a project in Andhra Pradesh for the National Highway. The rock was met at 5 meters or 6 meters. The scour depth was 10 meters, based on the soil at the top. Can the scour occur through granitic rock? That's it. Point I want you to, all of you, think. Please don't go by, I would request IRC to revise it, but we had to put pressure with scientific study, which is what I want our geotechnical engineers to get into. I wish I was back in a college, then I could have started all of this, but I realize now when I'm practicing that scour prediction is one of the most conservative, outdated ones in our country. Thank you.